Hello, quick introductory video on differentiation. I'm going to break this into different chunks so we can build it up. Differentiation is the area of calculus that was created by Newton and Leibniz, and what they were interested in is working out, particularly Newton was looking at the planets and how they were moving around. So they were moving in curves, and he was trying to work out information about these curves. And particular gradient was one of those things that interested him. You know, what direction is the planet traveling at a particular time? So let's have a quick look at this curve here, that green curve, and it's different to this straight line, isn't it? The straight line has the same gradient throughout. Here on the curve, their gradient, the rate of change, varies depending where you are on the curve. But if we were interested in this point here, we could find this tangent, this white line, which has the gradient at that point. And we might be interested in what were the sort of applications of this? Well, what's the rate of growth of your savings at a particular point in time? What's the acceleration of your car at a particular point in time or place? And that's what we need. It's the sort of instant rate of change. It's the instant acceleration. It's the instant growth. It's the instant gradient. And we do this by finding small differences. Hence we have this term differentiation, because we're looking at small differences. But for the purposes of this introductory video, I'm just going to talk about gradient, yeah? And we'll use that term. Okay, so let's have a look at an example of how we can do this using GeoGebra. So what I've drawn on GeoGebra here is a single curve, this green curve. It's y equals x squared. And I could put a point on it, point A, there it is. That's at x equals 3, so y is going to be equal to 9. And if I put a second point on here, it's called B, excuse me, I'm going to move that up here. So x equals 4. Then y is going to be equal to 16, yeah. And we can draw a line between those 2 points. If we drew just that section, it would be a chord, yeah. It's called a chord between these 2 points, yeah. And what we're interested in is how to create a tangent at this first point A. Well, as you can see, if I put the B over here, that's nowhere near a tangent, is it? But as I bring B closer and closer to A, I'm getting something that looks like a tangent, yeah? So when they're pretty well together, I've got something that looks like a tangent. So can you see that if I can get these points really, really close together, I can get quite close to creating my tangent line, and the tangent line, because it's just touching there, has the gradient of the curve at that point. So let's put the gradient on here, shall we? And let's go back to here. We started with these 2 points. So when B is at the point 4, 16, the gradient is going to be 7, isn't it? Because we come across 1 in the x direction and we go up 7 in the y direction. So we can see that the gradient of the line between these 2 points is 7. And if we bring B down, so it's about now 3.5, we can see that it's gone, the gradient's got, so the gradient's now down to 6.5, and as I come down, getting closer and closer, 6.2, 6.1, 6.0, yeah, so we're getting to around 6, getting very close to 6. Look, it's almost exactly 6 now, and we're close up. If we go by the point, it's gone to 5.9, 5.8, and as we go a long way away, it goes down to 3 there, yeah. So can we see that we're in this region here, we're pretty well at the gradient is 6, yeah. Okay, let's see if we can do some maths, a little bit of maths to prove that quickly by looking at our triangles. Okay, so here again we're going to do the curve y equals x squared, and we're going to start with our first point is at x equals 3, so y equals 9. And let's look at our upper point we started with, which was x equals 4, therefore y was 4 squared is 16. So we had our along was 1, 3 going to 4, and our up is 7, which is 9 going to 16. Yeah, and our definition of a gradient is our up over along, change in y over change in x. So that's 7 over 1 gives us 7. So our first gradient was 7. Now let's put these points closer together. So let's start with our first point being at x equals 3 and our second point being at 3.1. So now we've got a triangle with a base of only 0.1. Well, our y is 9 to start from, but 3.1 squared is 9.61. So our up is 0.61, yeah? So if we're finding our gradient our up over along, we've got 0.61 divided by 0.1, which gives us a gradient of 6.1. Yeah, so that's an exact value, isn't it, for our calculation? So we've gone from 7 to 6.1. What if I take our x values and make our triangle smaller now? So I'm still starting at 3, but now I'm only going to go to 3.01. So our base of the triangle now is only 0.01, yeah, hundredth. And 3.01 squared is 9.0601. So our up is now 0.0601. So our gradient is 1 divided by the other here is 6.01. So we've gone down from 6.1 to 6.01. Now let's make our triangle even smaller, shall we? And our x value is going to 3, and we're going to go up to 3.001. So we're only moving up a thousandth now, yeah? And 3.001 squared is this number here, and therefore the difference between the two is now 0.006001. So these two, the up over the along now is the value of that is 6.001. So if we have a look at our pattern of those numbers, we started with a gradient. When we went from 3 to 4, we had a gradient of 7. 3 to 3.1, we're now down to 6.1. Then it came down to 6.01, where that was 1, wasn't it? The base was 1, this one was 0.1, and that one's 0.01. This is going to be 0.001. So where do we think this is going when this is effectively that space has become really small? This triangle's become very, 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 very tiny. Well, the answer is it looks like it's going to 6, doesn't it? The gradient at this point looks like it's going to 6. Well, that's what we were looking at before. And now let's quickly see if we can prove that it's 6. Okay, exactly 6. Okay. So again, we're starting at our point 3,9, but I'm going to move us along just a distance h, yeah? So our upper point, the x value is 3 plus a little h. Think of it as a little number h, little h, yeah? And therefore our y value at the top point is 3 plus our little h squared. So how far have we gone up? Well, if we have a look here on the right-hand side, it's going to be the difference in the y values. There's our 3 plus h squared, take away our base 3 squared. That's our starting point, wasn't it? So if we expand this bracket here, you can use the grid method. We've got 9 plus 6h. Yep, that's the 3 times h, and we do that both way around, so we get 2 lots of it. There's our 6h plus h squared, and then we've got to take away our 9. So the difference, our y difference is 6h plus h squared. Yeah, that's our up. There we go. So let's, again, our gradient is up over along. So our up is 6h plus h, and we've got to divide it by our along, which is h. So the first term here is 6h divided by h, which becomes 6. That's a fixed number, yeah? And our second term is h squared divided by h becomes just h, yeah? Okay, so that's our expression for the gradient of this little triangle. Now, what we were looking at here is making triangles smaller and smaller and smaller and smaller and smaller. And so h gets smaller and smaller and smaller and smaller. And in practice, the reality is that when it gets really, really small, in effect, h is 0. So what happens to this expression when h is 0? Well, the first term remains at 6, and the second one is 0. So we're looking at our gradient. We've got 6 plus 0, which is 6. So we've proved that at the point x is 3, 9, at that point, for the curve y equals x squared, we've proved that the gradient at that point is 6. I'm going to stop there, and you can look at that, and I'll pick up and do another video to generalize this.